Internal combustion engines, as you probably know, aren't exactly the champions of efficiency. Take a modern gasoline engine in your average car. It only converts about 35% of the fuel's energy into actual movement. The rest? It's mostly lost as heat and noise. Diesel engines do a bit better at around 40%, but they need complicated and pricey emissions controls to be as clean as gas engines. So what's happening with all that wasted energy? Why can't we put more of it to good use? Here's the thing. A typical 4-stroke engine goes through 4 phases: intake, compression, combustion, and exhaust. Each one takes up the same amount of time, but only the combustion stroke actually does the heavy lifting of producing power. The others? They're mostly just along for the ride. If we could somehow stretch out the combustion stroke, giving it more time to extract energy, the engine would be way more efficient. Unfortunately, that's not how traditional engines are built, so a lot of energy literally goes up in smoke, or more precisely, it escapes as heat and noise through the exhaust. And get this, when the exhaust stroke begins, there's still so much energy left in the exhaust gases that they're under a ton of pressure, around 4 to 6 times higher than the air around us. That's why the exhaust gases practically fly out of the cylinder on their own, without much help from the piston. It's almost like they're in a hurry to leave. One way to make engines more efficient is by increasing the compression ratio. Now, this ratio is just a comparison between the smallest and largest volume inside a cylinder. If you imagine the cylinder as a space where combustion happens, increasing the compression ratio means making that space smaller when the piston is at the top and bigger when it's at the bottom. This change gives the engine more time to convert the fuel's energy into useful work. However, cranking up the compression ratio too much can cause problems. For one, if you squeeze the air-fuel mixture too tightly, it can ignite on its own, leading to an engine-destroying knock. And even if you avoid knock, a very high compression ratio creates super high combustion temperatures, which means more nitrogen oxide emissions, bad news for the environment. Plus, making engines handle these high pressures requires heavier, more robust parts, which can slow things down, especially in diesel engines. So, what if we could somehow make the combustion stroke longer? That's what James Atkinson thought when he designed an engine with a longer combustion stroke, which made it more efficient. But his design was a bit too delicate for practical use. Even Nikolaus Otto, the guy who invented the traditional 4-stroke engine, saw the potential in a longer combustion stroke. He teamed up with Gottlieb Daimler to create an engine with an extra cylinder that could harness the leftover energy in the exhaust gases, a kind of early version of a 5-stroke engine. Unfortunately, their engine didn't perform well, so it was eventually shelved. Fast forward over a century to 2003, when Belgian engineer Gerhard Schmitz revisited this old idea. He got a patent for a 5-stroke engine that was pretty much the same as Otto and Daimler's original design. And guess what? He managed to convince Ilmor Engineering, a serious player in the world of high-performance engines, to bring his idea to life. Ilmor, known for making engines for IndyCar, Formula One, and even MotoGP, took on the challenge. They've even created a marine engine that produces 725 horsepower while still meeting strict emission standards. While the road to more efficient internal combustion engines is full of twists and turns, engineers are still finding ways to squeeze out every last bit of energy, and that's pretty exciting. Engines are marvels of engineering, but let's be honest, they're not perfect. Take your average modern gasoline engine. It manages about 35% thermal efficiency. That means only 35% of the fuel's energy turns into actual power to move your car, while the other 65% just escapes as heat and noise. Diesel engines do a little better, clocking in at over 40% efficiency, but they come with their baggage complex, costly emissions control systems to keep them as clean as gas engines. Why can't we make these engines more efficient? The main issue is that in a typical 4-stroke engine intake, compression, combustion, and exhaust, only the combustion stroke produces significant power. The other 3 strokes? They're just wasting energy. If we could somehow extend that combustion stroke, letting the engine harness more energy, efficiency would skyrocket. Now, you might think the piston is the hero that pushes exhaust gases out of the cylinder during the exhaust stroke, but that's not entirely true. When the exhaust valve opens, the gases are still under a lot of pressure, about 4 to 6 times atmospheric pressure, to be exact. This pressure is so high because the engine didn't have enough time to fully harness the energy during combustion. So, these gases practically sprint out of the cylinder on their own, leaving a lot of potential energy unutilized. One way to boost efficiency is by increasing the compression ratio, which is the ratio between the smallest and largest volumes in the cylinder. A higher compression ratio means more energy can be extracted during the combustion stroke, but there's a limit. Push it too far, and you risk engine knock, where the air-fuel mixture ignites prematurely, or you end up needing heavier, more robust engine parts, especially in diesel engines. Not to mention, high compression ratios lead to higher combustion temperatures, increasing nitrogen oxide emissions, a big no-no for modern environmental standards. So, engineers have been on a quest to make the combustion stroke longer. Enter James Atkinson, who in the late 19th century came up with a design that did just that. His engine was more efficient, but the complex mechanics made it unreliable and unsuitable for high revolutions per minute. Even Nikolaus Otto, the father of the four-stroke engine, knew the limitations of his design and experimented with adding another cylinder to harness leftover exhaust energy. Another engine, with 3 cylinders, known as the Verbund motor, attempted to squeeze more power out of the exhaust gas by using a low-pressure cylinder to catch the leftovers. But like many ideas ahead of their time, it didn't catch on and was shelved. The design had a near-perfect balance, thanks to the symmetry of the pistons, and it relied on conventional technology, no need for expensive new parts or research. Ilmor even presented it at the 2009 Stuttgart Engine Expo, generating a buzz. But then, nothing. Why? 3 big reasons. First, the engine's displacement was a bit misleading. Officially, it was a 700 cubic inch engine, but that only counted the 2 high-pressure cylinders. The low-pressure cylinder wasn't included because it didn't handle combustion directly. If you counted that too, the engine was closer to 1.5 liter, making it larger, heavier, and more complex than initially advertised. Second, the energy left in the exhaust gas varies with engine load and revolutions per minute. At high revolutions per minute, there's plenty of energy to harness, but at low revolutions per minute, the exhaust gas has little to offer. This means the middle piston, designed to capture this energy, becomes a drag on the system, actually reducing efficiency in everyday driving conditions. Finally, by harnessing more energy from the exhaust, you reduce the heat and pressure available for other critical engine components, like the turbocharger and catalytic converter. Without enough heat, the catalytic converter takes longer to reach operating temperature, making it harder to meet modern emission standards. So, despite its potential, the 5-stroke engine joined the long list of innovative designs that couldn't topple the conventional 4-stroke engine. The trusty 4-stroke has been around for nearly 150 years, outlasting countless challengers. Sure, electric vehicles might be the future, but for now, the good old internal combustion engine isn't going down without a fight. Who knows, maybe we'll still be using some version of it for another 150 years. The 5-stroke engine is a fascinating idea that's still struggling to make a big splash in the mainstream market. Researchers and engineers are still intrigued by its potential, hoping that advances in materials, manufacturing, and computer modeling might help overcome its current limitations. But with the rise of electric vehicles, could the future of traditional engines like this be in jeopardy? This engine promises great improvements in efficiency, emissions, and power, but it hasn't yet been widely adopted due to practical challenges. As the automotive world moves forward, the future of the 5-stroke engine is up in the air. It's a prime example of how balancing innovation with practicality and market demand isn't always straightforward. Will this technology ever find its place, or will it fade into the background as electric vehicles take center stage? If you found this video informative, give us a thumbs up. We'd love to hear your thoughts in the comments. What do you think would happen if these innovations were introduced today? Would they still be considered cutting edge? Or would they be seen as old-fashioned? Hit that subscribe button to stay updated on all our latest content. And don't forget to click the bell icon so you never miss a new video. Thanks for watching, and we'll see you in the next one.